On February 11th, a big discovery was announced that researchers at the LIGO have detected gravitational waves for the first time, which is great. So what is LIGO? LIGO is the Laser Interferometer Gravitational Wave Observatory. And you can see, so laser, it uses lasers. Interferometer, the word meter means to measure, and interfer means interfere. So it's measuring the interference of these two lasers, or these two beams. And it's used to observe gravitational waves. And the instrument, the diagram is here. You can see that it's made up of some mirrors. It's got these arms. The laser comes in. There's a beam splitter. And essentially it's measuring the distance between these mirrors. And it's doing that by measuring the wavelength and how these two, the two beams from these mirrors are matching up at the photodetector. And it's so precise that it can measure changes in distance between the mirrors as small as a 10,000th of the size of a proton. So these mirrors are, over 2.5 miles long, and they can measure that small of a distance change between the mirrors. They're very, very sensitive to any type of shaking, any type of movement. So things that can cause the shaking: trucks on a nearby freeway, earthquakes obviously would cause some shaking, some movement of these. Also gravitational waves. Gravitational waves would actually stretch and compress the distance between these mirrors as these waves pass through the Earth. So what are gravitational waves? Where do these come from? Well, gravitational waves are a result of Einstein's theory of general relativity, which says that space-time is a fabric. Space and time are one fabric together, and it's affected by mass. Here's the equation. This is called the Schwarzschild metric. And the thing to notice here, there are 4 parts of this equation. And you see time, and r measures the distance away from a center. And you also see in the equation m. The m represents mass. So the thing to get out of it is simply this, that mass affects space-time. It affects the measurement, it affects the geometry of space-time. And so when we have a mass there, it is changing the structure of the space-time around it. So if we have an asymmetric object that's spinning, it would create gravitational waves. For example, 2 black holes or 2 very massive objects, them spinning around each other would create gravitational waves. And then if 2 black holes collide, that would also create very big gravitational waves. And so what the waves are is they're the stretching and contraction of the very fabric of space-time. Space-time itself is oscillating back and forth, so to speak. And so as these waves pass through the Earth would jiggle like jello. Granted, a tiny little bit, smaller than the size of a proton, thousands of times smaller than the size of a proton, but that's what happens. That's what the theory says will happen as these gravitational waves pass through Earth. Okay, so how does LIGO recognize these particular waves as opposed to a truck passing on the freeway? Well, for one thing, there are 2 of these observatories in order to help rule out local interference. One's in Louisiana and the other's in Washington. So if they both detect the same event, that means it's a cosmic event. It's not just a local truck going by on the highway. Another thing is that astronomers have certain patterns that they look for that are predicted by Einstein's theory. So they know to look for a specific type of data that they would get. And on September 14th, 2015, within milliseconds of each other, both detectors received this exactly what they were looking for. And you can see in that wave pattern on the right. Another thing that you'll see as you look at articles is this 5 sigma, the level of certainty. A sigma is a standard deviation in statistics. And so you can see in this diagram 34%, so 68% of statistics in a normal distribution in this type of curve fall within 1 standard deviation. 95% is within 2 standard deviations, and 99.7%, so almost everything, falls within 3 standard deviations. So 5 standard deviations would actually be out here. What they're saying is that these results are so precise, they're so good, that there are less than 3 millionths of a chance that these that this data was, or that these data were mere coincidence. It matches the theory so well that it's within this 5 sigma. And so if something is within 5 sigma, less than 3 millionths of a chance of mere coincidence, that is the gold standard for announcing some type of discovery. It's the same thing with the Higgs boson. They reached the 5 sigma standard, and then they were able to announce that they had found that just a few years ago. So what happened? 2 black holes spiraled into each other to form a larger black hole. One was 29, the other was 6 solar masses. That means each black hole, one of them was 29 times the mass of the sun, the other black hole was 36 times the mass of the sun. The resulting black hole was 62 solar masses, and the scientists tell us that all this information was encoded in the wave itself, the way that information is encoded on a radio wave. All this information was encoded in the gravitational waves that they were able to pick up at LIGO. Now, if you're doing the math, you're saying that there are some solar masses missing. So what happened? 3 solar masses worth of energy were lost in the form of gravitational waves at the moment of the collision. We also know from Einstein that matter can be converted into energy. E equals mc squared is that famous equation. And in the sun, the process of fusion, you have tiny little bits of matter being lost constantly, and that produces the energy that's in the sun, and all the stars, for that matter. There are 3 types of atomic bombs. One of them is fusion, the hydrogen bomb, and it only takes a little bit of hydrogen, about a party balloon's worth of hydrogen, to level a whole city. You can imagine what a whole sun of energy could do. And so 3 entire suns worth of mass were lost and created these gravitational waves at the moment of this collision. So that's a lot of mass. And then 1.3 billion years later, the waves produced by that event go through the Earth and are detected by LIGO in September of 2015. All right, and the signal is so strong, the scientists say they could see the data. Visually in the data, they could see that this signal had been there. And right away, they knew that they were onto something. So why is this a big deal? Well, first of all, it was predicted by Einstein by the theory of general relativity, so it's further support of one of the most successful theories in the history of science. It confirms that gravitational waves travel at the speed of light, which is something there was a question about. It also confirms that gravity has no mass. But another big deal here, you'll hear people talking about this ushering in a new era of astronomical observation. And the reason is that this was the first astronomical event not observed with a telescope by light. All the other information we've gotten about the outside universe we've gotten from forms of light, whether they're gamma rays or X-rays or radio waves, using all the different types of telescopes and gathering all those different types of light, microwaves for the microwave background radiation, all these different types of light. But this time we've gotten a different type of data, something that's not light. And if we can observe, so why is that a big deal? That's good because light can't pass through matter. So if I have some matter in the way between us and something else, then we can't observe that thing happening. That light isn't necessarily going to pass through a star or a galaxy or another planet or something like that. However, so most events are blocked from our view. However, gravitational waves pass right through matter. So we can observe, if we can use gravitational waves, we can observe things whether there are other things in the way or not. And so there's a lot more information available to us in the universe if we can use gravitational waves to gather data. And that has now happened for the first time.